Hello, I'm Giridhar Reddy. I'm from Chaitanya Bharati Institute of Technology, Hyderabad, and I was shortlisted for round 2 of Sparc Nano workshop at IIT.
Hello, I am Akash Agrawal. I am pursuing BTech in Electrical from NIT Bhopal. I am at IIT Hyderabad for Sparc workshop.
Hello everyone, my name is Tinanjan Nagar and I am a final year BTech EC student currently enrolled in CGC University Mohali, and I am very delighted to share that I have been shortlisted for round 2 of Sparc's Nano workshop, and thank you.
This is Dhanush Narayanan from NIT Trichy. I am from EC department. So through our institute courses we got to know about the chip aspect of design aspect of these chips, and here we got exposed to the fabrication aspect of it. So now we know the whole story. I would like to thank IIT Hyderabad and Government of India for this opportunity.
Hello everyone, I am Purnima Yadav from NIT Jaipur. I am a third year BTech student and from Electronics and Communication Engineering. I am here at IIT Hyderabad. I have been selected for Sparc Nano workshop.
Hello everyone, I am Adu Babraj of NIT Calicut. I was selected for the part 2 of NanoX program. Now we are here at Hyderabad, IIT Hyderabad. We had our classes and introductions till now. Now we are getting started with our projects.
So before entering the clean room, we have to remove our shoes. We have to wear our shoe cover, and also after coming here, we have to wear our gloves, and after gloves, we have to wear our hair cover, and after that mask. And the next procedure will be wearing our bunny suit, and after wearing the bunny suit, we will be covering our head using the head cover, or also we can use another separate head cover, and we will be wearing our clean room specific shoes, and this is the part we have to do before entering the clean room. This is governing process.
After we enter the yellow room, we see the optical microscope, which we use to inspect the developed patterns on wafers. We keep our sample on the stage, use the knob to position the stage without vibrations. We select an objective and adjust the focus using the coarse or the fine knobs, and we can get the live view through the Sense software. We can adjust the bright field or phase contrast, illumination, and we can directly export the image into the computer, which is attached to the microscope.
So now I will be explaining to you about the process of cleaning a wafer. So for cleaning a wafer, this is our wet bench. We use this to clean a wafer. So for cleaning the organic contaminants, we will be using acetone. We will pour the acetone on our wafer, and then we will put in the sonicator for 2 minutes for cleaning it, and then we will be using isopropyl alcohol for cleaning the metallic part, and then we will again keep it in the sonicator for 1 to 2 minutes, and then we will be using the DI water, that is deionized water, for washing it. That's how we clean a wafer. Okay, after doing the cleaning part, we will be doing a dehydration bake. So for doing it, we will be put our wafer on this and we will set the temperature to 120 degrees Celsius and bake it for 2 minutes. And then we will put our wafer on this spin coating machine, and we will put the photoresist on top of the wafer and spin it according to our recipe and how much thickness we want.
So this is the wafer cutting mat. On this we'll place our wafer and cut it. So it has many dimension line across it. Each line is almost 1 centimeter, and we put our wafer across like this, and from this is a diamond cutter. From this we'll cut our wafer. We place this cutter at the edge of the wafer, and it will cut across. This is another cutter. This is a glass cutter, and this is another diamond cutter. Now I'll be explaining about the dry etching process. This is done using 3 machines. The first one is Cobra, other is Polaris, and then we have the Estelis machine. So the Cobra machine is used for dry etching for metallic substances, and the Polaris is used for insulators, and the Estelis is used for DRI etching. Now Cobra and Polaris are used for the RI ICP etching. So now I'll explain about the Polaris machine. So the Polaris machine is divided into two main chambers. The first one is the lead lock chamber and other is the main chamber. So in the lead lock chamber, the pressure goes up to the 10 to power minus 3 torr, and the main chamber, the pressure goes up to 10 to power minus 9 torr. In the lead lock chamber, we use scroll pump, and in the main chamber we use scroll and the turbo pump. So first we'll take our wafer substrate and put it into the lead lock chamber for the cleaning purpose first, and that wafer will go inside the main chamber. After the pressure conditions of the main chamber and the lead lock chamber will match, the bowl will open and the wafer will go inside the main chamber. Now the O2 cleanup process will be happening, and it will take around 45 minutes at 60 degrees Celsius to occur. And after the process is done, we'll get a wafer outside again in the lead lock chamber, and then we'll take it out. And after that, we'll put over the main substrate on the wafer which we which we gave for the cleaning first. And now we'll put out the main sample which we have to etch upon that main wafer of silicon. And now we'll again put it inside the lead lock chamber, and it will go into the main chamber for the main etching process through plasma. This is the main control of the machine. Through this system, we'll control the recipe of the machine. In this machine, we'll give the control temperature, pressure, the speed, and everything we can see in this machine. And from here, we can give the step-by-step process recipe of the machine.
Okay, as you can see, I'm standing right front of the electron beam lithography, and in this electron beam lithography, we have a vacuum chamber in the left side, and in the right side there is the machine. So in electron beam lithography, it is generally used for the sub 10 nanometer fabrication process and for sub 10 nanometer fabrication feature size. In electron beam lithography, we actually use an electron beam, which is the electron source made up of the tungsten guns. And this electron beam has an electron power of 10 kilowatt to 550 kilowatt. Thanks.
Next, we have wafer bonder here. We use thermo compression method to combine two wafers by applying heat and also pressure. We use in an vacuum atmosphere, and also we have two different sides. We have precision aligned chucks which will be placed one over the other, and also we'll be having cameras and other equipment through which we will be doing the alignment. We'll also making use of other methods to make we'll be using different kind of methods to combine the two silicon wafers. Now we are in front of sputtering machine. So here we can see there are two different parts of the system. Here we can control the pressures and other parameters of the machine. We have a magnetron magnet here which we can use during the loading of the substrate. Here we can see a load lock chamber and a main chamber. Load lock chamber works at a pressure of around 10 power minus 3 to 10 power minus 4 bar, and the main chamber works at 10 power minus 9 torr. So there are some guns below. There are 4 guns which have target inside, and we majorly use copper, chromium and titanium metals to deposit on the substrate. We have a chuck on which we put the substrate. We load it on the load lock chamber. We put it inside the main chamber, and then we start the process. So we also have some digital systems which controls the whole process. We can see how much time is remaining. Generally, we put 800 seconds for a 80 nanometer of sample sputtering. And we also have a cryogenic vacuum pump which generates a very high vacuum of a magnitude of 10 power minus 9 torr. This is about sputtering.
Hello everyone. So I will be today explaining about the oxidation machine which we have present over here. So as you can see that I am actually standing in between the two oxidation machine. In the right side, on the left side of mine, there is a 3-stack furnace which is an oxidation machine, which means that there is the 3 tubes inside it, like horizontally placed. And in my right side, there is also an oxidation machine whose architecture is a 2-stack architecture furnace tubes. So it means that there is currently 2 tubes present in the horizontal position. So let me just go to the words. What is an oxidation is important. So oxidation is a process where we actually needed to build an SiO2 layer on top of my silicon wafer, and Why we need it? It creates an insulation for my silicon, and it is also creates passivation. So it is very much important if we build an SiO2 layer, and it creates us a very efficient command of MOSFETs. So let me just deep dive into the process, like why there are different two types of oxidation. One is wet oxidation and other is the dry oxidation. So in wet oxidation, we actually passing the HO2 like in a vapor form, like in the so it reacts and so it is a very slow process. And after that, we have a dry oxidation. Dry oxidation, we are getting used to the oxygen vapors. And on top of that model, there are two models between that oxidation process. Is the Dean-Grover model, kinetics, the working of the oxidation model. So we actually know that in an oxidation, we need to grow a passive layer of silicon dioxide. So silicon dioxide is needed on the top of the silicon wafer so that impurities do not trap over the silicon wafer. So as the silicon SiO2 layer grows on top of the silicon wafer, so it gets difficult for the oxidation during the oxidation process to make a silicon SiO2 layer on top of it. So exponentially the time also increases. So in this way there are different kind of models. That's why the architecture is different, so that the floor space also get reduced and we are getting efficient results.
So now we'll talk about the laser writer. So firstly we'll have to unload the stage. So once the stage comes here, we can place the wafer over there. So after placing the wafer, we'll have to place it in the center of the stage, and I mean like it has to be over the hole. After we place it there, we'll have to switch on the vacuum so that the wafer gets stuck onto the chunk. So that's important. So once this is done, then we can again load the stage. So after the stage is loaded, now here we have three lens. Okay, lens 3, 4 and 5. So we'll have to move the handle and place it over the corresponding lens. So usually we are going to be using with lens 3 or 4. So we'll place the lens correspondingly here, and we're going to choose the lens part here also. Here we can see that the substrate is illuminated by the red light, and usually the photoresist is not sensitive to red light, which is of nanometer 640, wavelength 640. So that is not going to be sensitive here. So now when we move on to the software, here we are using the laser writer software. So first things first, so we are talking about the sources. We have two diode sources. So one is the gallium nitride. So gallium nitride has wavelength of 425 nanometer, and the other one is helium cadmium. So here helium cadmium, we have a wavelength of 325 nanometer. So basically these two are the sources, and we have the stage, and this stage is compatible with 3-inch, 4-inch and even 5x5-inch wafers also. According to the device we are fabricating, there are many devices where we don't want to use solvent for cleaning purpose. There we use dry cleaning method like plasma. In this plasma, this is a plasma etcher machine. In this we are using oxygen. The pressure inside is 500 millibars. So in this plasma etcher we are using oxygen to generate the plasma. It is mainly used to remove organic contaminants. So the oxygen will flow inside, and with the CCP RF, it is converted to plasma, and it is used to clean the wafers and substrate, glass substrate or silicon substrate accordingly.
So now let's see about thermal evaporator. So firstly, before starting the evaporation process, like this is a physical vapor deposition process, as you might be knowing. So before starting this, the first thing is to we'll have to set some conditions. For example, the water pressure has to be 5 bars, and then we'll have to also check the dry compressed air levels and also the nitrogen levels. So once all of this is being set, we'll have to create a vacuum. Why do we need a vacuum here? So that we need a very high mean free path. So what do? We have actually two pumps here in order to enable this vacuum thing. And the first thing, it is functioned by a roughing pump or a scroll pump. So this will take us to a 10 power minus 2 to 10 power minus 3 torr. So, and after this, in order to go to high vacuum, which is required for the deposition, that is 10 power minus 6 to 10 power minus 7, we have a turbo pump which will enable this. So yeah, we talked about this thing. So then we have this heating source. The heating source used here is tungsten. So this heating source, we do the resistive heating in order to heat metals like aluminum, chromium, gold, silver in order to deposit on the substrate. So we are going to lower the substrate on the stand, and then we are going to start the heating. Once the vacuum thing is done, we are going to use resistive heating using tungsten to evaporate the metals. So once these metals go, they go and stick on to the cathodes.
the cathode is where the substrate is present. So once it reaches the cathode, it cools down and it nucleates and sticks onto the surface of the substrate. So this is how we are gonna deposit these metals on the substrate. And we also have a thickness monitor here. So the thickness monitor is enabled by the QCM. We have two QCMs basically here, and these two QCMs use the substrate equation in order to calculate the thickness using the quartz crystal frequency. So that's basically about it.